My name is Byungnam Kahng. A little bit. Okay. I'm going to talk about Kuramoto model with the inertia. Okay, so switching from applications, I'm concerned is the second order Kuramoto model with a mass inertia term, because this second order Kuramoto model has the inertia it shows this underdamping motion, so it's very difficult compared to the non-inertial first order Kuramoto model. So I'm concerned the two types of distribution of natural frequency. One is the unimodal, like Gaussian distribution, and the second one is a uniform natural distribution case. I work on this mixed order Kuramoto model also, but I think I cannot present this one this time. So I will present these topics in the next week in Florence. Okay, I consider the first case is the Gaussian distribution case. This second order Kuramoto model, exactly same one as the string equation often used in the electric engineering. So in this case, M corresponds to the inertia I of the turbine of the plant. The dissipation term. The PI is the power of the produced in the plant I, and this is the coupling term between two neighbor oscillator of two neighbor buses. So for swing equation is a little bit more detailed compared to this simple swing equation Kuramoto model. But we can apply it. This study provide us some insight to what the behavior would be in this swing equation in electric power grid. This problem is also related to the Josephson junction array case. This Josephson array has the second order from the types equation, but compared to this one, this omega I is constant for this Josephson junction array, so it's much a simpler case. I introduced some previous result studied by Tanaka et al. It's a long time ago, 1997. They concern the M very small case, M equal 0.95 and 0.2. We know that the M is equal to 0.95 is a little bit close to the massless case, but here so even it's the order parameter jump and it goes this way, and when it goes reversely, it exhibits the hysteresis curve. When M is a little bit bigger, then the transition point is a little bit different. So they argued that this second order Kuramoto model exhibits a discontinuous transition. Later, the Kahng et al. Studied intensively about the second order Kuramoto model. They consider the order parameter behavior as a function of a coupling constant K. Also, they examine the mean frequency profiles as a function of a K, and also the function of this is maybe omega here. So from here, when M equal a little bit bigger, M equal 5, when the dynamics proceed in the forward way, and the other parameter jump and oscillate. In the backward way, oscillate continuously decrease and drops at this transition point. This relationship means that there exists some cluster of the synchronized cluster. This is called the central or primary cluster, and there is some gap. For the first order Brownton case, there is no gap in this figure. In the second order case, there's a jump, and this one. This is the case for very small m. When it's a little bit bigger, then there exists the secondary cluster here, so very tiny. So in this work, recognize that there exists a secondary cluster, synchronized cluster. So in this paper, published chaos solutions request this year with the collective, we consider of the dynamics mechanism. So we consider the theta dot, average theta frequency versus C omega. Omega is the natural frequency. When t equals 0, then this is a straight line. It some initial condition of the frequency as the natural frequency. And when the time is a little bit fast, then we found there's some primary cluster here, and also there's secondary and tertiary, quaternary is an infinite number of plateau observed. When t is much longer, these steps more distinct way. So we were wondering how such a step case occurs. What's the feature of the step cases? That's our main goal. What we found that synchronized cluster dynamics emerges before just to concern the order parameter behavior, but we found that the primary cluster once primary cluster occurs, and later the secondary cluster not simultaneously, sequentially. So we wondering what's that. The second, when there exists some interaction between clusters. So once this primary cluster occurs, then primary cluster attract other oscillators. So it's the suppress of formation of the secondary cluster. So when the omega is enough grown, then the secondary cluster occurs, but still the primary clusters attract these oscillators. So the small oscillators move back and forth between the first primary cluster and the secondary cluster. So this dynamics is kind of very critical. So we found that it follows the power behavior. So once the primary clusters is fixed here, the other clusters avoid staying around this cluster because they have a more fast natural frequencies. So secondary clusters and higher order clusters stay here. So velocities here is very small, very fast, and their velocities here is relatively slow. So they coherent at this position and make some ordering. So here is a primary cluster and secondary and tertiary and quaternary. So if we measure the gap height, they made a rational number. So because they make a resonance effect with each other. This is so it's a parallel to positions. They form a resonance effect, and then the number of the frequencies we show this ratio, and there are many high order cluster, multi-cluster form as a Debye cases, and the boundary of the dominant analytically determined. This is I will show you. And we examine this is the time, this is the frequency. We consider three cases, m equal 5 and 6, k equal 6. This is the same k. These two have the same mass. So if we compare this and this with this different mass, then we found that the plateau size is bigger here, and plateau size is smaller when n equal 8. Because the mass means that the kinetic energy is much bigger, so the oscillators want to move the other cluster, and they make a secondary cluster, so that when m equal bigger, even though the coupling constant same, because the kinetic energy is dominant, so that the primary cluster size is smaller. If you have the same mass, but the coupling constant is bigger, then because of the potential energy of the coupling term, so the primary cluster is bigger, but instead the secondary cluster size is smaller like this. This is the kind of energy conservation case. So when it's not easy to. This is the, for example, when the first primary cluster occurs, then secondary cluster appears very late time, and when the secondary cluster begin to grow, then kinetic energy decreases suddenly like this, and so on. So there is some competition between the primary cluster and the secondary cluster. So as the natural oscillation frequency is bigger to grow, to make a form, then the secondary cluster, as the secondary cluster appears, the first primary cluster decays suddenly, so there's such a kind of competition occurs. We check where the most oscillator locate, and we found that there is a 108 degree, and this one, so the appear very deep opposite side oscillators state here. So to understand this behavior in an analytic manner, we consider that this term is regarded as a tau I, and tau I is divided into the terms of each cluster. This is a primary cluster, this is a secondary, tertiary, and so on. And to determine the size of the primary cluster, we consider only this one, because the secondary cluster appears later. So then this Kuramoto model becomes simpler, and then we obtained this one. I will explain more detail about what MM means later. And next time, so we consider only the coarse-grained term. So this is a coarse-grained manner. So coarse-grained second-order Kuramoto models enable us to obtain this kind of very complicated analytic solution. Okay, so I will not detail explain this one. When m equal very large, about m equal 10, then it's very interesting. because the kinetic energy, due to the big kinetic energy, the primary cluster size shrink and shrink as m equals increase. So that when m equals sufficiently large, then the primary clusters becomes shrink, and eventually it destroyed. So that the black plateau is dismantled and absorbed in the secondary cluster like this. And there are two ways: it disappear or it remain. But when it remain, the first primary cluster still plateau exists, but the oscillators belonging to the primary cluster is dismantled, but it's oscillate between two clusters, the secondary cluster. So it's oscillation between two clusters. But so that if you measure this quantity, it appears like a plateau, but it oscillates like this. Let's move to the uniform distribution case. So nature frequency distribution looks like this. Then also this is a Gaussian distribution case. This is a uniform distribution case. The order parameter is the stepwise increase and eventually jump. There exists many plateaux like this, not like this. This is big one and small one. This is cluster size is very uniform. As k is increased a little bit more, then it is still uniform. Then its size is bigger, and this gap is also increased. If we look at this one with the average frequencies time, then this is as time increase, it goes this way, and shrink. This means that cluster with a large velocity merge, the smaller one goes this way, and eventually it goes this way. Let me look at a little bit more. The order parameter r as a function of k, then it increases stepwise this way, but there's some transient regime and synchronized state. And we can introduce we apply the Manycoff criterion. Manycoff criterion means that we just compare the friction term and the supplied form, and if the balance is determined by omega m, that is Manycoff frequency. If omega is omega less than omega m, then this way, then that means that the oscillators in continuously oscillate. Otherwise, it's emerged to the central clusters. So, but if you look at carefully, then the order parameter increase, not constant with k. So roughly, if our order parameter is equal to k, then this boundary is proportional k. So this area is the boundary. Okay. So as k is increased, the boundary is increased, and also there is a slope here. So from here, if we increase k, then there is some separation between this one. But if we increase the k is large enough, that this Manycoff domain merge at here, and these two clusters merged and make a bigger cluster. And these two cases as well, the Manycoff domain increase with the coupling constant k. If the domain meet here, then two clusters merge and goes this way. Due to this mechanism, clusters go this way. Also, there is some resonance effect between the clusters. So due to the resonance effect, there are this merging case occurs. So Manicopo criterion clusters merging occurs. Resonance effect arise due to the some competition between the clusters. Okay, so I have to stop here. Thank you.
Thank you again.